Hey everybody. So we're still, we've been talking a lot about vectors in recent videos, and we're still in that world. So we've built a bunch of tools up, just general understanding of vectors. How do we add, subtract, multiply, those kinds of things. We made our dot products and cross products. So now let's start using some of this stuff to describe things that are important to us. One of the first things, the first thing we're going to start with here is a line. How do we describe a line using some of this vector language? So I've drawn our three-dimensional coordinate system here, and I've dotted in a line that I want to describe. And just like in 2 dimensions, what do you need to have, what do you need to know a line, right? You need to know a point in space and then a direction, right? So if I have a direction, right? Let's see if I'll show my pen. If I have a direction, right, but I can have that direction at many different places, and you'll be talking about many different lines, like parallel lines. And if you just have a point, there's an infinite number of lines through that point. But if you have both a point and a direction, there's only one line that does that, right? So here's a picture of the line that we want to describe. So let's say we know one point on it. Right, and I'm going to call this point P naught. Give it coordinates x naught, y naught, z naught. So that's a known point. We have that point. And let's say we have the direction in the form of a vector. And so I'll call this vector v. Okay. Now, a quick question you might have is, how long should v be, or something like that, right? Well, there isn't really a good answer to that. V is not unique. You might notice, for instance, that v could be pointing the other direction, and it's still pointing along that line. What I want to do with vector v is be able to describe every point along this line somehow. And any v pointing in parallel to this v would work. It will change how the equation looks slightly. But it will be at its essence the same thing. So we'll see how that is in just a moment. So here's what we're going to do. I'm going to draw a vector from the origin to that point that we know. So I'm going to call that vector r naught. It's the direction vector for P, right? And so from the picture, I have r naught must be equal to x naught, y naught, z naught, right? Just looking at what I've drawn here, it's a vector pointing at the point P naught. Now, suppose I want to describe some arbitrary point out here, right? Any point along the line. So I've drawn it over there to make my drawing easy, but you can think of this as any point along this line, right? Let's give that a name, a vector. Sorry, not that point, but let's just define a vector that I'll call r. That's equal to whatever arbitrary point I choose on that line. Okay, so what I want right now is a vector equation that describes every point on that line, meaning I can somehow change the equation to describe this point, or this point over here, this point over here, anywhere along this line. So if we look at this picture, how do I get from r naught to this point? I have to add a vector, right, along the line. Okay, maybe I'll draw this in with a little dotted red to make it show up a little more, right? And if I take r naught plus this vector along this line here, if I add them together, I get r, right? So r will be equal to r naught plus this vector here. But what is this vector? Well, it's a vector pointing in the same direction as v, but scaled appropriately to hit this point, right? In other words, I'm going to use t as a scalar here, just some number t. If I take r naught and add a scaled version of v, I can hit any point, right? Remember, this is an arbitrary point. So for instance, if If t was 0, we're hitting the point we started with. If t is 1, we'll hit this point right at the end of v. If t is 10, we'll hit some point out here, adding 10 copies of v. Maybe that was too far. If t is negative, we'll start having v pointing in the other direction, and we'll hit all of these points. So by changing t, we can scale it appropriately to hit every point along that line. And so this is the vector equation of the line, okay? Right. And it's relatively simple to see. There's our point, this is our direction, right? The two things that we said we needed to have. This picture, I think, is pretty important to understand because it's pretty easy to construct this formula if you need to, and it helps us understand what it is we're describing, right? We're ending up, remember, this vector equation, if I choose a value of t, I don't get points on this line. I get vectors pointing at points on this line, right? This vector r is, if I take this and add it up, I get this vector r here, which is a vector pointing at the point, right? So it's a little different than the point itself, but it's very well related. We can also write this in component form. So remember, r is just x, y, z. Let's give some symbols for v. Let's say that v, I'll just say that v is a, b, c, right? These are just going to be some numbers. Well, what's going to happen? R naught, we have x naught, y naught, z naught, plus t times a, b, c. Using scalar multiplication of vectors, I can multiply t to each of these. So we'll have TA, TB, TC. And then I can do vector addition to get x naught plus TA, y naught plus TB, and z naught plus TC. Okay, so there is the same equation in component form. Okay, this is something that we haven't talked about explicitly yet. I don't think I've talked about it in these videos. But this is a vector function. We're inputting t, and the output is a vector. So our input is a single number, and our output is a vector. If you remember way back to parametric equations, our input was a number and our output was a point, right? It's a very similar kind of thing. Again, slightly different. The parametric equations described points on the line. We're now describing vectors that are pointing at points on a line, right? And you might think that the distinction is a little bit silly, and sometimes it can feel that way. And sometimes we cheat a little bit in the way we talk or move around things. But there is a distinction, and we have to keep them distinct in our minds for the times that it won't matter. So this is what we call a vector function. We'll talk about those in more detail eventually, but this is an example of one of those. Inputting a number, outputting a vector. We can also define parametric equations using this, right? If instead of describing the vectors pointing at these points, I just wanted the actual points, I could have three parametric equations. X equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct, right? These would be parametric equations giving us the points on L, our line L, right? Whatever we've decided to call it, okay? So let's do an example to make this a little bit more concrete, and then we'll actually take a look at a little animation of what this looks like. So let's say I want the equation of the line. Let's find equation of the line through the point -1, 5, 9. And in the direction of the vector I hat plus 2j hat minus k hat. Right, so I've written this vector as the sum of basis vectors, our standard basis vectors, I hat, j hat, and k hat. if you remember what those, right, I hat is 1, 0, 0, so this sums up to a vector with a 1 here. The j hat is 0, 1, 0, but there's a 2 there, so this thing together is 0, 2, 0, so we get a 2 here, and then minus 1 for the k hat. So that's what that vector is. So looking at this, all I need to do, right, I'm trying to write down r equals r naught plus tv, okay? So what makes sense? R naught, remember, is a vector pointing at some point on the line, right? So for instance, this point, right? -1, 5, 9. V is the direction that the line is going, and we've been given this as 1, 2, -1. Again, now I want to point out, both of these are choices, right? We could describe the same line choosing a different point and a different direction vector, right? The point's just going to have to be any point on the line. The direction vector is always going to be parallel to this, right? So it could be, you know, negative v would also work, 2 times v, 1.793 times v. All of those will work. It will just change which value of t's correspond to which point on the line. I'm going to make the easiest choices, use the point given and the vector given. So now I can just go ahead and write that this r is a vector that points at any point on the line, is given by r naught plus tv, which in this case is -1, 5, 9 plus t times 1, 2, -1. Or we could write this as, let's see, -1 plus t, 5 plus 2t, 9 minus t, right? Just adding those two vectors together. Okay. So let's take a quick look at what we've built here with a nice little animation I found online. Let's see. Yeah, here we go. So what we're looking at here is we've got our 3D plane. So here's our x-axis, our y-axis, z-axis going up. This blue line is the line in question. And we see what this is doing is animating through values of t. If you look up in the upper right-hand corner, you'll see the x, y, and z functions that are given. These are actually the parametric equations that are spitting out this point that's traveling along the line. But what it's graphing for us, right, as values of t change, this black line, this black vector is the vector r pointing at points along the line, right? And so it's moving with the point for each value of t, right? So remember, we've got our vector function, r is equal to r naught plus tv. This animation is showing you values of t. This is all written down over here. The values of t in this particular animation are going from -15 up to 12, right? So when it starts back here, that's the point that's spit out when t is equal to -15, and the black line is the vector that's spit out when t is -15. If we look at when t equals 0, right, that would spit the point r naught to us, right? If you put 0 in for t, you get 0 there. I don't know that I can pause this one, so we can't quite stop it there. Oh, maybe we can. Let's see what happens if I can do that. Maybe it doesn't pause. Oh, there we go. We can stop the animation. So for instance, let's put in 0. And now it's pointing at, that's the original point. So here's the place where we kind of built this whole thing. This is our point P naught, right, which was -1, 5, 9. It's a little bit hard to see, but it's going back in the x direction 1. It looks like it's above, you know, it's back in the x direction -1, and then up, then along the y-axis by 5, and then up to about, it looks like that looks to be 9 right there. And so that's the point when t equals 0. And anytime we scale by some value of t, for instance, when we write t equals 1, we're going to take the vector v, right? With the vector v in our case was equal to 1, 2, -1. I'm not going to try to draw this accurately, but we take the vector v and add it to this black vector, and we'll get a new vector over here. Okay, so when we turn the annotation off, when we change our t value to 1, oh, I got it almost exactly correct, completely by accident. We see that we've now, if you can remember the vector that was here, r0, is now we've added this red vector that I drew to it, and we've landed at this point over here. And so that's the idea. And as we scale through, or as we scroll through all these values, we get every single point on the line if we're looking at the parametrics, or we get a series of vectors that point at points on the line. Okay, let's do a couple other things with our example. Let's see, let's go back to paper for a second. Let's do a quick exercise with this, showing that we don't actually have to, how this is not unique. What I mean by that is, let's take, for instance, I'm going to take we chose the vector v to be 1, 2, -1. Over here, I could look at the vector u and make it equal to, let's see what I did, 2, 4, -2. So notice this is just a scalar multiple of v scaled by 2, so I've doubled the vector. And so let's call, I'm gonna add a little notation to this. I'm gonna call this R1. This is one vector equation of this line. With this other vector u, I could write a different equation, R2, which is going to be very similar. It's going to use the same point, right? It's going to be R2 equals R0 plus TU instead of TV, where U is just a multiple of V. And so this will end up looking like -1 plus 2t, 5 plus 4t, 9 minus 2t. Okay. So now notice what happens when sorry, I should use a different parameter since it's a different equation. I'm going to change this to an S, so this is clearer, although maybe that you'll disagree since I have to write over it. So I'm changing the parameter over here to S, pardon me. So when S equals 1, let's see what happens. R2, I'm just putting in a 1 for S. I get -1 plus 2 spits out a 1. 5 plus 4 times 1 spits out a 9. 9 minus 2 times 1 spits out a 7. And let's come over here and see what happens when t equals 2. R1 spits out the values. -1 plus 2 gives me 1. 5 plus 2 times 2 gives me 9. 9 minus 2 gives me 7, right? So it spit out the same point, just at different values of its parameter, right? And so that's what happens when it's not unique. You get the same points, but they don't happen corresponding to the same parameter, right? Typically, this won't matter very much for us if we're just trying to describe the shape of a line. However, there are cases where it will matter if, for instance, you're trying to describe the motion of something specifically. You want it, for instance, at t equals 0 to be where it starts, and at some other time to be where that object's supposed to be at that time. We'll talk more, we'll do some examples of that at other times. It's not a huge shift, right? You'd have to do a little manipulation of these to make it match what you want to match, if that's the case. But for the geometric object, these are equivalent, right? They're describing the same set of points, they're pointing at this exact same set of points, okay? All right, let's do another thing with this line before we go. This will be one last idea. So let me rewrite what we have. We've got this line. I'm going to just stick with our first equation. R equals -1 plus t, 5 plus 2t, 9 minus t. Okay, that's our equation. So notice R is spitting out a random point. So let's give this the name xyz is equal to -1 plus t, 5 plus 2t, 9 minus t. All right. And we said we could write this as parametric equations by saying, well, instead of pushing out the vectors, let's push out points whose x, y, and z coordinates are given by the components of this vector. Right? So these now are symmetric equations spitting out points that correspond to the places that this vector is pointing at. Okay? So that's a way you could describe that set of points. When we did parametric equations in only 2 dimensions, we eliminated the parameter and we could get you know, y in terms of x or x in terms of y, depending on which direction was easier or more convenient for us. We can't quite do that here, but we can do something related to that. So if I solve these equations for t, for instance, this one becomes x plus 1 equals t. This one becomes y minus 5 divided by 2 equals t. And this one becomes 9 minus z equals t. Right? Well, all 3 of these expressions in x, y, and z are now equal to t. So it must be the case that x plus 1 equals y minus 5 over 2 equals 9 minus z. Okay, and this is another form of the equation for this line. People often call the equation for this line. It's kind of a weird thing to say with all these different kinds of equations. Anyways, this is another way to describe the line with what we call symmetric equations. Okay, in general, these symmetric equations, let's say the symmetric equations for a line through x naught, y naught, z naught in direction v equals a, b, c. These can be given as x minus x naught over a equals y minus y naught over b equals z minus z naught over c. Okay, so that's just what we did here, right? We just had ones down here for our direction vectors. I guess this one should be z minus 9 over -1. I did the algebra and got rid of that negative. But it's essentially the same thing as this. And one question you might ask is, wait a second, we're dividing by a number. There's no reason that the number doesn't have to not be 0. And that's true. So in the case, let's say, for instance, if a was equal to 0, right, then we wouldn't be able to do what we did here, right? The symmetric, the parametric equation for x would simply have been x equals x naught plus 0 t. And so we can't really solve for t in this case. In fact, this disappears. So in the case that a was equal to 0, our symmetric equations would just look like x equals x naught, and then we have the other 2 portions of this symmetric equation, right? What does that mean? Well, let's see. What is that going to look like? That means our line, let me draw. Here's my x, y, z. If every point on this line has x equals x naught, right? So if this is some value of x naught, right, then this line has to live in the plane, right, where every point, you know, it could be some point through that plane. I know this is not the greatest drawing, but if you imagine a plane perpendicular to the x-axis, so the x-axis is piercing this plane at that point, the line has to live in that plane because that is the plane where every single x coordinate has the value x naught. And if you move off of that plane, you don't have this anymore. So that's what that picture ends up being. Okay, let's stop there. We'll do more videos on this topic with some examples to get a little deeper into it, but that is it for now. Thanks, everybody. I will see you next time.